What's up, Warriors? Good morning, early on a Friday morning, and I wasn't planning on doing this, but I'm going to do it because you asked. So, this video, we're going to cover the Bombtrack squad drive agony that y'all went through this week. We're going to go through a little bit of set up some main concepts so that you've got something to watch. Now, some things before we begin. We're going to go through, quote, problems, but the main thing you want to develop is your ability to solve problems, not just one little set of problems, kind of one trick pony kind of thing. No, that's not what warriors do. Warriors solve problems in general. So we want to look for those things that we can generalize, those skills, that knowledge that we can generalize from this specific set of problems, which is comprehensive in nature, to a larger set of unknown problems. So, in other words, we can handle anything. So what you're going to need to begin this is a couple things. Number one, you're going to need a chicken. Number two, you're going to need to remember and have a good to solid foundation about populations. Remember, we have big populations. We have those populations that we can get access to. That's you all down here. And I can go from general to specific about the different composition and the nature of this and the performance of this. Okay? Or I have different populations here that are greater. Maybe in this population, I can get the data and the performance and the characteristics, but it's going to take me quite a long time. And then even here, maybe the globe, maybe the region, maybe the nation, I really can't. Even if I wanted to. Even if I wanted to spend every waking hour, I couldn't. Okay? So again, sample is what we do to make a guess about how that is behaving. We take a tiny little piece, and based on that piece, we do one of two things. We either decide if that sample is behaving in the way we think the population is, or we abandon what we think the population is doing, and we develop a new belief based on what that sample is doing. So this sketch right here, you might want to watch this a couple times and just think about what is a sample, what is a population, okay, and feel pretty confident that you can do that. So that's one thing that you need. Another thing that you need is a healthy dose of some kind of warrior drink. Obviously, that's legal, some kind of water, coffee, all the above. Just keep yourself going. And most of all, you need that warrior mindset that even though the stuff might be difficult right now, you're going to grind through it, because with every grind, with every investment of sweat, blood, and potentially tears that you put into this, you will gain strength with every single part of that investment, and it is all worth it. All right, and the last thing you need is a knowledge of the Bombtrack problem, okay? So that, because I'm not going to go through all that right now up here on the screen, but I will try to go through a little bit of it. Okay, so first and foremost, we've got our question, which is our situation, which is the Joker said he's going to bomb Gotham City. The mayor obviously is very concerned about this, but Batman knows the Joker, and he knows he's up to no good. So he doesn't necessarily get intimidated by this threat, and of course Batman doesn't get intimidated by anything. That's why he's Batman. But Batman knows that he's got to drop some science with Defiance to figure out what's going on and call BS on what's happening potentially. So we cruise on down here to Q1. Before I jump into Q1, I want to talk about the forest and the trees. So, boom. Oh, by the way, you just got to bear with me. I'm rolling hard. I'm rolling rough. I'm rolling free. 30 days in the hole. I don't even know what that means. Well, I do know what that means, but not in this context. The point is, I'm not going to have time to edit this video. So we just got to roll with that. Okay, the forest and the trees. Here's what I'm talking about. Let me grab my little spread. Let me draw it simpler. So when we're talking about this block of problems, we have 3 forests. And this is the strategic decision you need to be able to decide to make when doing any given problem. Number 1, am I dealing with a single value? And there's keywords for that. Things like, in this case, a bomb. The Joker's going to detonate 1 bomb. 1. Okay, so that's a keyword. 1 or a, or just 1 value. Not a sample, 1 value. So this is a forest, a single value. Next, we have samples and sample probability. And in this forest, we have 2 major forests, subforests, but we don't want to get in the trees yet. Okay, we have our friend X bar, and we have our friend P. Okay, now remember our big back tattoo. This is not a forest, this is our back tattoo, where we have the population and we have the sample. Multicolor. So when we talk about the mean for the population, we write that as mu. When we write about the mean for the sample, that is X bar. When we write about the standard deviation for the population, we write that, the technical term is the circle with the line across. We could call that sigma and kind of raise our game a little bit, I'm just saying, you know. Anyway, and then when we talk about the standard deviation for the sample, we're talking about that beautiful letter S. Kind of like, I don't know, Shatskin or Scranton, or you get the idea. Okay, and then finally, we're talking about this mysterious thing called the proportion, which tends to kind of mess people up, and we'll talk some more about that. But within the population, we're talking about this dude, which is not the life of pi. It is what I call P-pop, but it's simply the proportion of the population. 46% of all women like to have flexibility in their jobs, according to a global survey. That kind of thing. And then over here, we just got simple old P. Not P protein, but just P. So this back tattoo, man, I don't think Pro Ink is okay. I wouldn't even recommend that you go to Pro Ink right now. Kind of a bad idea, but get this somewhere, put it in front of your bed, and you wake up in the morning, put it where you lift weights, put it on the back of the cereal box. You get the idea. Okay. So we got to remember all this stuff, and this stuff is fundamental and contributes to our ability to understand samples and populations. Just going to do a rough erase because I need this space. You know what I'm saying? All right. Sorry about that. Because it doesn't go with the rest of my conversation over here. Okay, remember I was talking about forests, right? And so I have one more forest with this block. And that is the confidence interval forest. Okay, and over here, my subforests, again, am I dealing with trying to do a confidence interval for the population mean or the population proportion? All right, so I'll just make the analogy here that, You're like this warrior. Yeah, I don't know if you've heard of these guys, smoke jumpers. And what they do is I think, I'm not an expert on smoke jumpers, I've never done it. I got high respect for them. I think what they do, like out in areas of California where we have wildfires, very common. So, what they do is they parachute into these burning forests and they probably chop trees down. They do some crazy things to prevent fires. So, you're up here. This is you up here in this chopper. Get to the chopper. And you're flying around over these forests and you're trying to figure out which one is on fire, which one you're going to jump into. And so that's the strategic problem. You don't want to go jumping into some forest that is the wrong forest. Okay? So looking a problem from here on out until we do this exam thing. And even beyond that, you got to frame your thinking and confine your thinking to this right here. Okay? Don't jump into the forest and into the nuts and bolts. You might be in the wrong forest. Using the wrong formula, using T when you should be using Z, and all sorts of crazy things, okay? So you got to frame problems this way and make sure that you know what you're looking at. And yeah, the nuts and bolts of how you solve the problem is important, but if you jump into the wrong forest, you're not going to be able to fight your way out of that one. Okay? So this is paramount. Now, and I'm going to go through this, in the Bombtrack, in question 1, we are dealing with this forest. In question 1. In question 2, we're in this forest, a little bit here. We do a confidence interval, but we're mainly here. And then in question 3, I think we're here. And in question 4, we're down here for that proportion. Let me just double check on that real quick. Always wonderful to have a Word document up on the screen. Let me just jump into it. Okay, so question 1, one of the experts counseling the mayors, Dr. Walter Heisenberg. In case you didn't pick on that, that's a little reference to Breaking Bad. Walter White has an alter ego of Heisenberg, and so I kind of combined them. But Heisenberg actually comes from quantum physics and the uncertainty principle. But back on track. So looking at this, Dr. Heisenberg says, oh, well, the Joker's best bombs represent this other population of World War II bombs, and those bombs followed a normal distribution with a mean bursting radius of 17 miles with a standard deviation of 3. There's population mean and population standard deviation. So based on that, we can do some single value probabilities. So let's go back to the whiteboard and do question 1 relatively quickly. All right, so question 1, sorry about that. We know we're clearly in the single value X forest. Boom. Okay? And we're so confident we're not going to worry. I mean, we're just going to shorten our thinking and our scope to single value X. It doesn't mean we don't think about other force that might be burning right now. Okay, but right now we're just going to narrow our focus to single value X. So Gotham City is 20 miles in radius. Okay, so we know that the Joker's bombs, according to Heisenberg, who, oh, by the way, might just be a plant by the Joker. But we don't know that right now. So a mean bursting radius of 17. That's what that is. That's what Heisenberg is saying, is that these bombs follow this kind of population with a sigma of 3. And so the Gotham City is 20 miles in radius. So that essentially is our single value, or not our single value, but that's what we want to compare things to when we start looking at probabilities. So I'm just going to hang 20 miles over here. That's the radius of Gotham City. So based on the assumption above, what is the probability that the Joker's bomb could affect the entire city that has a bursting, if it has a bursting radius of 20 or more? All right, so the first question wants to say, what is the probability of a bomb being 20 miles or more? So we have a single value, x, and we want to get a probability. So to do that, we're going to use this formula. We first need to determine a z-score. And so we're going to take that single value x minus the population mean and go over sigma. And that is 20 minus 17 divided by 3, which gives us a z-score of 1. Now, when we go to the z-table, we know a z-score of 1 refers to a probability of 0.8413. But we're asking a bursting radius of 20 miles or more. So whenever we do an or more problem, we're going for this probability. The 0.8413 refers to that probability. So we're going to do a 1 minus to get the probability that a single value x, a single bomb, could have a bursting radius of 20 or more. And 1 minus 0.8413 is indeed, what do you think, chicken? What is that? Okay. That is 1586. So that is the probability that the Joker's bomb could affect all of Gotham City. Nick Hager identified that, interpreted that very well. Okay? Single value X problem. All right, moving on. My magic wipe, disinfected, and all that. Q1B, what kind of problem with this? Well, again, I apologize. I don't like the way this is written. But we can work with it and identify what kind of problem it is. The mayor wants to evacuate the city, but understands the risk, or wants to understand the risk of not doing so. So what's the bursting radius of a bomb, bombs in the top 95.05? Well, really what I wanted to say was what's in the top delta of that, so whatever, 4.95%. But the bottom line is this is still a single value problem. What would be the bursting radius of a bomb? Okay, so we don't know what single value x is, but we do have a probability of 4.95. Okay, so there's a couple ways we could do this. The simple way is to go into to take this 95, because it'll get you the same answer. Okay, there's a way we could do this in Excel, but I'm just going to set this up here. So first things first, within this forest of single value, okay, remember that's the forest we're in. So the probability, or the tree that we want to chop down there, smoke jumper, is we have a probability and we want to get a single value x. That's what I call the reverse problem. So that probability we have is 0.9505. Okay, so the first step here is to shrink down like Mike TV and get inside that table that Z table, and walk around until we find that number right there. And then we're going to find a Z-score and fight our way out of this flipping table and get big so we can go get swole. I digress. So let's do that. All right, we're going to shrink down here and we're going to get inside of this and we're going to walk around until we find that 0.9505. Where is it? Where are you? I'm not even Irish. Why should I try to sound like? It's been a while since I've had Lucky Charms. There it is. All right, 0.9505. So what Z-score is that? Well, we look over here to the left, 1.6. And we also know that we're smack dab in the middle of this table, so we got to look up. So we look up, and there it is, 0.05. 9505, 0.05. So that means that we are going to take the Z-score of 1.65. Remember. We have to remember this when we get big and get out of that table. And boom, we go back here. So 1.65 is our Z-score. Get big out of that table. And before we forget it, we're going to write that sucker down. Okay, to do this, where we have a probability and we want to get a single value X, I don't know why I put SI, like Sports Illustrated. I don't even read that magazine. Okay, whatever. So Z is going to be 1.65. To do this, we're going to use the formula. We're solving for single value X. That's what we want to know. And we're going to use this formula. Z times sigma plus the mean. So 1.65 goes here. We remember from old Heisenberg that this is 3 and this is 17. And assuming we have our chicken, we get the answer of 21.95. So, shake it off. What does that mean? That means that is the bomb in the 95th percentile. That and higher. That is the value of a bomb that's up in that range of probability. Okay? At the 5% and a little bit of change, the radius, not range, of the bomb is 21.95. Bam. So that's Q1B. Onward to QC. There are several 8 mile wide, kind of like Eminem, 8 mile, dun, dun, dun. Anyway. Several 8 mile wide areas of Gotham that could be quickly evacuated. What is the probability of the bomb's bursting radius would be 8 miles or less? So once again, we have a single value X, and we want a probability. Okay, we're still in single value X forest. Okay, haven't left. So we have this, we want that. Well, this is the same as Q1A. All right, we still have these givens. Okay, so we're going to use this formula. We're going to first establish the Z-score. So we're going to go back to this. This time, X is going to be 8. So we're going to go 8 minus 17 divided by 3. And boom, boom, boom. My chicken consults me from a distance. This is -3 of the Z-score. Now, I go to my Z table and I look up -3. And that, a Z of 3, refers to a probability of 0.0013. Now, I'm good. I mean, I like probabilities in terms of decimals, so I'm good if you say the probability is 0.0013. You don't have to convert that into a percentage or anything like that. Because I know that when we say something is 0.99, I can compare those two, or even 0.158, whatever it is. So this is the probability that this will be 8 miles or less. And I'm going down here, I'm drawing a line, 17. Check it out. I just lined right up. That's so awesome. Small victories. Yeah. So that is that right there. So it's small. Okay. 8 miles or less. Boom. All right, we can move on. Q2. Maybe we're in another forest, maybe we're not. So the question is, over the past 6 years, the Joker has attempted to detonate bombs around the world. Batman has been able to capture the bursting radius of 9 of these. Okay, so Joker, over the past 6 years, he's bombed all sorts of places. He's bombed here, he's bombed here, he bombed here, etc. Batman has been able to capture 9. So he got this one, maybe there's some other ones he didn't get, to the tune of 9. Okay, so, a smaller piece of the whole, that looks like that, which indeed it is. So if you're grounded in the concept of sample and proportion, you can identify that and drop some science with defiance. So let's keep moving. If Dr. Heisenberg's assumption about the Joker's bomb production from question 1 are correct, so that means that Heisenberg says a mean of 17 out here in this population of red and a sigma of 3. So if those are correct, what is the probability that Batman's sample mean is greater than 20 miles? Okay, so what does that mean? Well, that means that if we take out each one of these, the bomb radii that comprise these 9, that would be 1, 2, 3, 4, etc., 5, 8, and then 9. So we're going to average those. And what is the probability? We call that X bar. Okay, that will be greater than 9 or 20. Okay, that's what the question is asking. Because again, we're concerned about that radius of Gotham, and it's 20 miles. All right, just getting so excited that up in here, getting kind of hot. Wow. Sorry, Charlie. Okay, so that's what we're looking at. Well, the minute we see, shake, 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 the minute that we see this, okay, and we see this, we should identify that force that we're in, and that is the sample probability forest. We surely know that we're no longer in single value. I don't see a single value up on the screen. These aren't single values. That's not a single value. That's not a single value. And like others have pointed out, even more simply, this is not a sample size of 1, which is what a single value is. This is a sample size of non-1. So we know we're in this forest. And because we're in this forest, we got to use some different formulas, but the methodology is generally the same. Sorry again. I think there's a way that I can grab large parts and erase, but I just don't know it right now. Okay, so we're going to use a formula. We're trying to determine a z-score first, and then we're going to convert that into a probability because that's what the question is asking. So for this, we're going to use this formula where we say z is equal to x bar minus the mu over the sigma divided by the sample size. That's our setup. And that means we're going to put, mu is still the mu. We'll put 17 there. We're going to put 3 here. What's new? When I was a kid, I watched this show called The New School Review, coming right at you. They had this little catchy thing. I don't know if I really liked the show that much. I just liked it. Anyway, we're going to put that sample average 20 here. Remember, that's a sample average. That's x bar, okay? And then we're going to put the square root down there, which is 9. Okay, and we know that this turns out, we don't need to talk to the chicken. I think he's asleep. Are you kidding me? Anyway, that's going to be 3. That's going to be 3 over 3. That's going to be 1, so this whole thing's going to be 3. So we have a z-score of 3. And we know that's going to be, even before we go to the z-score table, that's going to be a low probability. And here it is right here, 0.9987. But we're going to take a 1 minus of that. Okay, because we're going larger, greater. What is the probability that that sample mean would be 20 or greater? Okay, so we're doing that 1 minus. We're going to get out of this z-score 0.9987. We're going to subtract that from 1.10 million zeros, and we're going to get that. So again, it's the number is the number. What is most important is put that into interpretation. The probability that the sample mean, the average of this sample, being greater than 20 or greater, is very, very, very low. Don't put that on the exam. Go ahead and take it 1 yard further and say 0.0013. So I'm just going to jump to 1 Bravo, okay? Now 1 Bravo, remember that 0.0013. Okay, so first we had a single bomb probability based on Heisenberg, standard deviation of 3, population mean of 17. We had the probability of 20 or greater being 0.1589. Now we have some sample data. We have an N of 9. And so Batman's sample average, and we want to know the probability of it being 20 or greater. And that turns out to be very, very low. So what this is saying is that the probability of this mean being the population mean and the bomb being greater and greater is really very low. This says that if that average, okay, if this is saying the probability of this average is low, then we begin to see that this here may not be valid. We're starting to question this because it looks like if the mean's not that, then the mean may not be that for the population. It may be lower than that. So we're starting to collect doubt. That's what Q1 Bravo is getting at. Let's look at Q1C. What is the probability that Batman's sample mean is between 17 to 21 miles. Okay? What is the probability that the sample mean is between 17 and 20 miles? So we want to know the probability of this interval right here. Okay? Well, we're still in the forest of sample probability. We're in the subforest of the sample mean. That we want that to be clear to ourselves, right? Forest. And the tree that we're chopping down is what I call a between tree when we're dealing with probabilities, with means, sample means. Okay? So I'm just going to do the setup. All right? So, again, our givens, we know Heisenberg, even though we're starting to doubt him by now, says, oh yeah, the population proportion or mean is 17 and the standard deviation is 3. Sure they are. So our setup is going to be, we'll grab that 20 and run with it. We already did, so we kind of don't have to do this again, but we will. And then we're going to do this down here for that. Okay. Put that 3 there. Again, our sample size is 9. Okay. And then when we get down here, well, wait a second. The minute we get 0 in the numerator, we don't need to mess around with what that is, because 0 divided by anything is a z-score of 0. Okay? And this, I think we just did. We did. We did this from the other page. And we got a z-score of 3. And we know that 3 corresponds to 0.9987. So, we already have that. So remember, a z-score of 0 is not a probability of 0. A z-score of 0 refers to a probability of 0.5. Well, let's check it out again. See, way up here on the corner of my table, or at least the front side of my table, z-score of 0 straight up, 0.5. So, with all that in mind, we have something that looks a little bit like this. That minus that gives us this. And so this is the probability of the bomb sample mean, okay, that Batman hasn't determined yet, being between those two. And so you're kind of going, okay, well, couldn't he just determine what the sample mean is? Sure, and he is going to. He's Batman, he can do anything. But the point is, he kind of wants to have a reference point of what that sample mean should be before he computes it. And this is so he can see if that sample is behaving with what we think the population is doing. This is very important to conceptually understand. Because if that sample mean is not behaving in accordance with this, maybe something new is going on, or maybe this is faulty or wrong, or maybe Heisenberg is really Harley Quinn in disguise. Okay, early in the morning. So let's drive on to Q3. All right, let's check out what Q3 looks like. Ha! Surprise, surprise. Batman decides not to trust old Heisenberg's assumption about, quote, the population of the Joker's bombs. Instead, he estimates the mean of the bursting radius based on the data he has available. Now, I know, Cameron, you're out there somewhere and you're going, you told us he had a sample size of 9, and I'm looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 values. So, what's going on, Chief? Well, you're right. When I wrote this problem originally, I was moving fast, and at the risk of making a bunch of excuses, I made a goof. And I was trying to like get the bombs to spell out Joker by their bursting radiuses, like the letter of the alphabet and all this other kind of stuff that just really, I think at the end, nobody cares about except me. So I goofed. Once again, that is the incredible rhyme animal making a mistake, but we'll get back on track. The bottom line is we have 13 values, and we go on to Q3 alpha. To estimate the radius of the bomb, Batman decides to build a confidence interval. So let's stop there for a second, and let's back up and identify our wonderful forest that we're jumping into. And the minute we hear the words confidence intervals, we are confident that we are about to jump into the forest of confidence intervals. And we know that we're going to jump into the subforest of confidence intervals, got to be able to say it to do it, of the population proportion. All right, so when we not only know the forest, we know the subforest. Now, this is about to get tricky. So it's important, once again, that we know where we're jumping into before we chop down the wrong tree. To estimate the radius of the bomb, Batman decides to build a 95% confidence interval. Okay, super. What should he tell the mayor about the bomb's bursting radius? Well, that would be the confidence interval. Okay, so let's review our givens. Well, we're in confidence interval land. We've abandoned these ideas or givens about the population, and that's what Batman is doing. He doesn't trust Heisenberg, so he has to use his sample statistics to do this right here. So he's going to take first all these numbers that he's been given right up here in this graph. Okay, so can I write on my screen? No. Great. Well, maybe, can I? Okay. I didn't really want to do that, but fine. So can I do this? No. But I can do this. All right, so he's gonna take those and these and these and these, and he's gonna add all those together. That's 13 numbers. Okay, so he's gonna get whatever that sum is, or go phi sig. He's gonna add all that stuff together, and he's gonna divide by 3. Okay, and that indeed is gonna be his x bar. So lo and behold, when he does that, his x bar is 9.23. Okay? And then he's going to do the same thing, and he's going to determine the sample standard deviation. Okay? Now, let's go down. How do I get out? I got myself in. I can get myself out. All right, so you're probably going, I can't remember how to do the standard deviation. Well, no problem. He's going to take all these numbers and he's going to, you can. Batman doesn't, he uses Excel, but he can do this kind of stuff in his head. Us normal human beings, not so much. So we're going to go back to our own version of the Batmobile, which is Excel. I can hear my sponsorship ringing right now. Just kidding. I can't imagine who would be sponsored by Excel. I mean, you'd have to be a pretty high roller to do so, and I'm probably not that guy. But in the meantime, bam. All right, so I put my numbers into Excel. This is A way, and I go down here, and I'm looking for that, as Lexi would put it, that point S, boom. And I'm going to highlight these numbers. And I think I'm going to get something like 1.34 or something like that. 1.23, 1.23. I could round. If I'm working all in Excel, I don't have to round until I get to the end. And so that's where I get the standard deviation of the sample, which we refer to as S. So back to my handy dandy board. Let's clean this up a little bit. We know we're doing a confidence interval. We have this is 9.23. This is 1.23. I think, just bear with me on my math. And remember, I counted up those variable or those measurements in the sample. Just slow and low, that is the tempo. All right, and let's get this out of there. Back to live. Okay, now what? Oh, I'm doing a 95% confidence interval. Okay, well, there's one big thing I need to realize here. The key thing is that Batman has said, I don't care what Heisenberg says, I'm abandoning this idea of this. The population, golly, we're 7 in the world. The population mean being 17 or the standard deviation being 3. I'm abandoning that. So you see that we don't have a standard deviation for the population. That is the $500,000 question. When we don't have that, we're going to use this, and that cues us to the formula we've got to use. And that formula to develop the confidence interval is going to be X bar plus or minus, and we're going to use the t distribution. So a value of t for alpha half, we'll come back to that, times the sample standard deviation divided by n. Okay, so when we're dealing with this right here, our alpha, 1 minus 0.95 is 0.05. Just keep rolling with that. If we took that in half, that alpha half is 0.025. Okay? So, when we go into the t-table, we need to be ramped up with two things. One is my pen is possessed by Darby Hetrick, a D3M warrior of the past that is saying hello. Hi, Darby. Miss you. I hope things are going well for you. I haven't talked to you in a while. I know. It's because I don't come down to the grum. All right. So, I need two things. I need this degrees of freedom thingy, okay, which is simply n minus 1. And in this case, that would be 12. And the other thing I need is this dude, alpha half. Got to have those two things before I go into the t-table. 12 alpha half, 12 alpha half, 12 alpha half. Here I go. That's not the t-table, so be gone with your bad self. That's a video I did for something else. So that's not a t-table. Where is my t-table? There you are, my little friend. Boom. 12, so big, can we go bigger than that? I know we can. Come on. Slow is, well, it's a little bit better. All right. So I'm cruising on down here looking for 12. Boom, there it is. Alpha half 0.025. Not 0.25, no. 0.025, there you are. 2.179. 2.179. 2.179. So 2.179. Let me get myself some space. Don't need this anymore. Sorry, Charlie. Back in black. I hit the sack. Don't you know what's... Oh, 2.179. S, 1.23. 13 square root. Sounds like a messy square root, but whatever. X bar, 9.23. So my confidence interval is going to look like this, but don't be crazy or lazy. Just be Jay-Z. I don't know. Get the ball in the end zone. This is not what a confidence interval looks like. All right, this is all jacked up anyway. All right, here's what a confidence interval looks like. All right. All right, I'm gonna write that sucker up here. Okay, and I'm gonna use the chicken to help me out. So I'm gonna do this 9.23 plus, forget about that minus for a second, especially since it's on top and it's wrong, plus all this jazz, which, I don't know, I could just call whatever, okay? I'll just call this whatever right now. So I'm going to figure out what whatever is, and I'm going to park that value somewhere. Looks like whatever is actually equal to 0.746469. Yep. Okay. So I'm going to park whatever, and I'm going to take 9.23 plus whatever, and that's going to equal 0.9 or 9.977 and I'll give you guidance. I don't, those kind of decimals just kind of hurt my head. And that's going to be over there. Okay? And I'm going to put population mean right smack dab in the middle. Because I don't know what the population mean is. I've abandoned Heisenberg's. I'm taking a guess at what this population mean is to the tune of a 95% size of a butterfly net. That means that I'm going to try to catch, or Batman is going to try to catch, 95% of the possible values for the population mean. He's not going to catch all of them. He's not going to catch 99% of them. He's going to catch 95. Okay? His lower value is going to be 9.23 minus whatever. And so chicken tells us that that value is 8.48 and some change. 675,309. And this right here is what he tells the mayor. Says, all right, mayor, since I have to do this for you. And oh, by the way, Batman kind of does this in his head while he's like jumping off a bridge in the Batmobile and ejecting it and getting onto a plane, which Batman has done, which actually one of my favorite stories, but I digress. So Batman says, hey, mayor, look, here's what we know, and here's what I think, based on science. This bomb is somewhere in between the mean of this bomb, of all the possible bombs that the Joker has made, is between 9.97 miles and 8.48, which is a lot less than 20, brother. See what I mean? And so, Batman, the mayor, question B in this problem, Batman wants a more accurate estimate. Okay, so let's think about this conceptually. If we want a more accurate estimate, we actually want this number to get bigger and this number to get smaller. That would give us a narrower range of what the population mean might be. We don't want this to get wider, because then we'd have a less accurate idea of the range that the population mean could fall into. So when we go this way, we actually need a confidence interval that is less. So we would need a 90% confidence interval. And you may be going, well, wait a minute, that means he's less confident. No, it doesn't mean Batman is less confident. Batman is Batman, dude. He's always confident. It means that the statistical definition of confidence, it means he's going to capture less of the potential values for the population mean. But actually, we don't care about the values he's not going to catch, because they're on the outlier anyway. When we draw this, and I'm just going to go bye-bye. When we draw, come on. When we draw this, okay, when our confidence interval gets narrower, we actually get a narrower range of idea around the mean, okay? Which I think also the other part of QB of this question B is, well, how does he get more accuracy? Well, if Batman had more time, he's currently got a sample size of 13. Sure, he'd want to increase his sample size. If he did that right there, then his curve would look more like this. But the Joker's about to bomb the city. He doesn't have time to do this. So really all he could do is narrow his confidence interval and express what that is. Okay, but the bottom line is, I don't even know if he needs to do that, because the interval he has, the high end of the range, isn't even exceeding 10 miles in radius. And everybody's got this fear that it's going to be 20 miles in radius and hurt all of Gotham City. And really the best the Joker could do is hurt about half, is what Batman is putting together. So the next question, C, is the mayor says, you're Batman, you're always confident about everything. Why aren't you confident now? Well, the mayor, obviously, I hate it for the mayor, because he's just kind of talking out of his fourth point of contact, and he doesn't really know what he's talking about. So the definition of confidence has nothing to do with how confident I am if things are going to happen subjectively, my opinion. This is an objective scientific definition, which is very simple. When we take our friend the Hack Daddy, This end goes off, sorry, Dad, but infinity does exist, and this end goes out to infinity, and this end goes out to infinity. So when we're talking about the area under the curve and trying to capture all of these possibilities, okay, well, we're not gonna, we can't go, I mean, how can we go out into, yeah, see, my computer won't let me. I can't go out to infinity. It isn't, quote, possible. Okay, so I kind of got to call it a day somewhere. And where we do that scientifically, okay, we're D3M warriors, we call that at the 99% point. They say, oh, okay, that's good enough, dude. All right. And oh, by the way, why do I care about this tiny little, tiny, way the heck out here, 10 miles out here? Why do I care about that anyway? I don't, because it's an outlier. It's like Dr. Dre, okay, or Spud Webb, okay, or somebody way the heck out here. It's like Ant-Man, this tiny little thing that really doesn't make that much of a difference. What I care about is understanding central tendency. Okay, I'm not trying to understand everything. I'm trying to understand on average what happens. Because if the curve is symmetrical, if I know the central tendency, that will probably be good enough in most cases. So, Batman says, I'm Batman, you'd kind of need to go back and refresh yourself, and so on and so forth. You got the wrong definition of confidence, bro. Moving on to question 4. So let's take a look at it. At the same time, Batman wants to know how many people will actually evacuate Gotham if the mayor wants to order an evacuation. Alfred finds out, he does a survey. Okay, and we got to be careful because sometimes the survey is about the population, sometimes about the sample. But he says, hey, will you evacuate Gotham? If ordered to do so, yes or no. And the results he gets back is 439 people say yes, 675 say no. Well, we know that even without knowing the specifics about Gotham City, that the amount of people that live in Gotham City is a lot more than the sum of these two numbers, which is that. Okay, so this is a population proportion. This right here is N. That's the total amount in the sample. So we want to know how many people will not evacuate the city. The question asks for a confidence interval of the 99% confidence interval for the proportion of people, P-pop, that will not evacuate the city. Okay, so we know that our interval is going to look like this once we're done. Okay, and we need to find what that value is here and what that value is here. I'm just going to give myself a little bit of space for your face. Okay, we have that given. So right away here, we know that alpha is 0.01 and alpha half is 0.005. Because that divided by 2 is that. And with population proportions, we can use a z-score. And so the z-score that corresponds to that probability is 2.58. And we can get that off our Mike TV table as well. Okay, so we're going to use this formula. The CI is P plus or minus a different form of whatever, Z times the square root of 1 or excuse me, P times 1 minus P over N. Okay? So, big thing that tricks people up, let me get this out of here, is what is P? Okay? Well, remember, P is the characteristic we're interested in, which is in this case, the amount of people who don't want to evacuate, which is 675, divided by N. I'm just going to jot this up here. P is X, characteristic we're interested in, divided by N. Sometimes P might be given to us. Super. In this case, it's not. So, I think the chicken is going to tell me that he's still sleeping, but I can communicate with the chicken while he sleeps. And the chicken tells me that this number divided by that number is indeed 0.6059. So I'm going to put that there. I'm going to use that all in this mess. I'm going to use 1114 down there. I already talked about what I'm going to use as P. As Z, I'm going to use that 2.58. I'm going to figure out whatever is. In this case, whatever is 0.0377. So this number over here, that plus this, 6436, and this is 5681. Nice, pretty, clean confidence interval for the population for proportion, the kind of thing I would want to see underneath the Christmas tree on Christmas morning. Maybe not. But the point is that at the 99% of confidence, the population proportion for the number of people that would leave the city if ordered to do so is less than 64% and greater than about 57%. So let's just think about what that means. More than half the city would probably not leave, even, if they were ordered to do so. Wow. So that means if the mayor wants to evacuate the city, even if he wants to do that, it's probably not going to be in a very effective decision because people aren't going to do it. So, Q5, the grand finale. What does Batman tell the mayor? Well, whether to evacuate the city or not. Well, let's just look where we were just. Let's talk about where we just were. Let's take a. Sorry. All right, some points of logic. People to the tune of roughly 56% will not go. Okay? That's what our confidence interval tells us. The bomb, as the population mean for the bomb, is somewhere in between, I think, 8 on the high end to 9 on the low end, which is much lower than the radius of Gotham. And the probability of one bomb, or even as we go higher in our sample size, the probability of the bomb being above 20 gets lower and lower. It really doesn't, it gets low pretty quickly. It gets to that with only a sample size of 9. Okay, so this right here, the idea that the bomb could affect the entire city is potentially a smokescreen. I begin to wonder if Heisenberg's a plant, what the Joker is trying to do. Maybe the Joker is trying to create fear, surprise, surprise, get an evacuation, and then he can do all sorts of things. He could pillage Gotham City, he could infect Gotham City with something else, and just cause mass hysteria. So maybe what we want to do is do something like, okay, this is Gotham, all right, and this is 20 miles. Okay, maybe we want to try to guess, and the bomb, really, we're talking about this, okay, is 8 miles, 8 to 9. So maybe we want to do partial evacuations. Maybe we want to evac this area, okay, and not evac this area. That's a technique. Okay, it's the Joker, so nothing is hard and fast, but we still have to do some more investigation. But the overall conclusion of Q5 is don't do a full evacuation of the city because the threat is not so great. Don't be passive. Batman's never passive, but it's just a matter of pinpointing what actually the threat is so that we can proceed in the right manner. So that's the rundown of the Bombtrack. Hope you enjoyed it. Hope you get something out of it. Remember, a couple things. Don't be confined to one set of problems. That's kind of like a one-trick pony that can do a couple things. I guess that would be a couple-trick pony. Think more general. Think about the forests of problems. All right, back to wherever I had it. I don't want to. Here we go. Think back to this forest. What forest am I jumping into? Single value, sampling, confidence interval. This is what I call recognize. You got to recognize and prosecute. This is on your canvas from a couple days earlier this week. I think it's Tuesday, the 24th of March. Any more of the days will seem to be the same. But the bottom line is figure out what forest you're in first, and then and where you need to go with that. If you're in the wrong forest, you're kind of hosed. All right, so figure out the right forest, and then figure out the tree that you need to chop down, and then go from there. Proportions, nobody likes them. Not nobody, but many people don't like them. The real trick is making it so you like them. Okay, they're a little bit different at first, but once you kind of understand and can segregate, okay, how do I determine what a proportion is? It's going to be a decimal. Even if you get it at a percent, it's going to be a decimal. If I say 60% of, quote, all people like vanilla ice cream, you need to just turn that into your mind. That's a population proportion of 0.6. If I say, hey, I talked to 20 people, 10 of them like Motley Crue, that would be a sample proportion of 0.5. So develop the ability to take those percentages and quickly turn them into decimals, because if you put that percentage into the formula on the numerator anywhere in there, it's just going to gank up your whole formula. All right, it's kind of like putting, I don't know, baking soda into your car. It's just not going to run anymore. Okay, I don't know why you. Anyway, so remember those key things. Don't be confined to these problems. Use these problems as a little bit of a training ground to grow stronger and to develop those mad skills. We will talk to you soon.